graphically speaking, same thing we had before, negative infinity world, all the way to the negative 4. Oops. Go the other way. And then so that's just a little review again on the inequality definitions of the boards. The next one, if we have polynomials, we cannot forget the very first thing I would love to be able to do, besides recognize the end behavior, because that helps me know where I'm supposed to start and where I'm supposed to end. But it also would be helpful for me to find the what's. Well, if there was an asymptote, that would be good. But I don't have an asymptote on this one. What are the things we want to find so that can help me draw my polynomial? The zeros. Yeah, we want to find the zeros. So I have to GCF it. And if it doesn't GCF, then I can do my rational root theorem, set up synthetic substitution or division. So in this y less than or equal to quantity x cubed plus 2x squared, I have a GCF of x squared. And remember, when you're finding your zeros, you could be treating this like an equation, right? So I want to look for x squared is equal to 0, because I'm setting y equal to 0. And then x plus 2 is equal to 0. I get x equals 0 and negative 2. And I'll just be careful that here, what am I doing on this 0? It's a double root, so that means I'm going to bounce. And bounce off of that one. All right. So graphing from, when do we do this? Chapter 2. Okay. Chapter 2, when we graph them, we would know our end behavior. It's a cubic. Lead coefficient is positive. It's supposed to start on the left down and end on the up right. And I'm going to go through 0. Actually, I'm not going to go through 0. I'm going to bounce off of 0 for one of my values, and then I'm going to go through negative 2. And then the only thing that's different between this and chapter 2 stuff is now we're going to figure out where do I shade. Once I have my curve, do I shade above that curve, or do I shade below that curve? Okay. And that's, again, what this is going to help me determine, the less than or equal to or greater than. There are two things that inequality is going to help me do. Know where I shade, and then the little line or not a line. So the little bar underneath determines whether I have a dashed, what we call boundary line, or a solid boundary line. So if I've got this or this, I have a solid boundary line. And if it doesn't have that, then it's a dashed boundary. All right. So let's see what happens. Let's graph this thing using my zeros and my behavior. Oh wait, that's not what you want this. Oh no. All right. I'm going to erase this, and let's just see if it allows me. Probably not. It's not going to be a smart board. It's going to be a dumb board again. Oh, wait. All right, so we're going to graph y equals x cubed 2x squared, hopefully. There you go, smart board. Way to be smart. There it is. Starting low, ending high, bouncing off of 0, which is a double root. You should have been doing that. And going through x equal negative 2. All right, so where do we go with the shading? The boundary line is solid, and it already is, because of the fact that I've got the less than or equal to. So where am I going to shade this thing? There are two ways to tell how I'm going to shade. probably the best way is to you can just pick a point to test it. And then once we get comfortable with this stuff, then we'll see, like if it's set up in a standard form like this one is, right? Y by itself. Then I can think about if it's pointing left as a less than, I'm going to go below the graph. And if it's greater than, I'm going to go above it. But let's say we don't remember that, or we just want to make sure. We can test a point. And let's test a point that's not on this boundary line. So how about 2, 0, which is to the right of the curve. We're going to test 2, 0 and see what we get. If we get the inequality to be true with 2, 0, then I'm going to shade on that side of that boundary. And if it's false with 2, 0, we'll go on the other side. All right. Y is less than or equal to x cubed plus 2x squared. Plugging in 0 and 2. Let's see what we get. Is 0 less than or equal to 8 plus 8? 0 is not less than equal to 16. This is false. I mean, yes, it is. It is true. What an idiot. This is true. So because 2, 0, which is here, is true, I'm going to shade on that side of my boundary, which means all my shading will happen over here. All right. So everything over there would be shading. And again, because it was in that standard form, I knew it was a less than. I shaded below any. That's the only difference between what we're doing from last chapter to this chapter is we introduced the shading.
Shade the entire right side or just the lower right?
You know, if you're feeling like you need to be artistic and you want to shade everything to the right, you go ahead. If you just did this little line thing that I got going on, that's fine. If you had the cool tool of a smartboard, you could do fun things like this. Oh, yeah.
I set my smartboard here.
So you could do that. But you don't have that cool tool probably here. Well, you're welcome to come here if you want to and do them in this. So, any questions on A, boundary lines, B, shading? Because the other stuff has really been what we had been doing before. Find the zeros and the NPs. That seemed pretty simple. Pretty much a review from, gosh, who knows when. All right, well, what if we have now a system? And we kind of had a similar problem. We will definitely have system problems with inequalities on our fun times, but we had a similar problem on the last fun times as well, right? Where we had two equations, and one was quadratic or cubic, and the other one was linear, and we've seen where they happen to intersect. And it's the same concept with inequality, but your intersection is now where shading of both polynomials overlap each other. And I can just shade that area. So do we remember what a y equal to a negative x would actually graph as? What is that? All lines are straight. Right? It is a line. And where does it start? Okay, so yeah. Okay, I can pick any value of x, and it's going to be the same value of y, correct? Opposites, though. So negative 10, 10. It's just y equal mx plus b, where the b is a 0, and your slope is negative 1. So I can start at 0, and then go down one, right one, down one, right one. And that would be the graph for this. So graphing that guy, we would have 0, 0, and then down one, right one, down one, right. And we keep doing that. Now, boundary line wise, the VL, what is it? Is it solid or is it dashed? This was dashed. Now, what does that mean? You guys even know what that means? It's the besides the fact that it looks like a bunch of hash marks. Yeah. That is correct. So if I happen to be looking for value on the boundary line, it would not satisfy the inequality. That's correct. All right, so we get our line here. Oh, thank you very much. About an E. And we draw a line. Voila, da-da. Boom. Now I have an arrowhead on that both directions. This one doesn't have the arrowhead because I hate when I do that. But anyway, it should be going both directions, right? Arrowhead lines. All right, the next boundary line. Let's do that one. So what is this guy? Okay, well, what is it? What's the shape? It's a parabola, right? This is quadratic, and the boundary line on this one is also dashed. Now, I could, as Ben was saying, we could go ahead and make it into standard form, ax squared bx to c. Can I use it in this form, though? Yeah, because this is in, what's this form called? Vertex form. This is in vertex form where I can actually physically see a couple things here. One of the things I can see is the hk, which is your vertex. And in this case, my hk is -2, 0. So there's my vertex. And because we have a vertex, we also know axis of symmetry. So have an axis of symmetry at x. So if I were to be graphing this thing here, we know that I have a vertex of -2, 0. We'll go ahead and put a starting point there. It's going to be a dashed line because of that boundary line. And now in terms of what the other points, you have a couple different ways of coming up with the other points, but I'm just going to go ahead and talk about our critical movements. And yeah, you're going to need to remember this stuff for our generic parent function. So our critical movements of the parent function y equal x squared. Do you guys remember this stuff? All right. Left 2, up 4, left 1, up 1, right 1, up 1, right 2, up 4. And then I would alter these depending on if I have a stretch factor vertically or horizontally, and if I have a reflection going on, and I have none of those happening. So what I can do with these movements is to simply apply them at the vertex at -2, 0, and go left 2, up 4. So left 2, up 4. There I am. And left 1, up 1, and right 1, up 1, and right 2, up 4. There are the points that I can draw my graph. If you don't remember that, you can just always put in a t-table, just pick some x's and find the y. You can do that as well. But anyway, we get something that looks like this, and it's dashed. Oh, what a fine-looking parabola that is. And then now we have to just simply determine where is this system, if it exists. We're going to see if this system has any overlap. So let's go back to the y greater than -x ground and thinking about where would the shading be. If we go to the rule, I meant kind of a slope-intercept form with a linear function. Greater than means I'm going to go above the boundary line. And above boundary line, how you can do that is put your pencil on your boundary line and move up. And that way it's above the line. The other thing I could do is test a point not on my boundary line, like say 2, 2. Put a 2 in for y and a 2 in for x, and I would get a situation that's true. So in terms of the shading for the dashed linear part, I have this. Above the boundary line. Now for the quadratic. Where would I be for the quadratic? This one says to go less than. And again, I'm going to be thinking about below the curve. I can test a point. I can test another point. Let's say -6, 0. It is 0 less than 16, and the answer would be yes on that one. And so the shading for the blue graph is going to happen here. That's below the curve. So we want to see all the shading that is overlapping. And the shading that's overlapping would be, let's see, highlighter. Yeah. So it's all of this area over here. Right? All of that would be overlap. And then it looks like I have this area over here also has overlap. Did I miss anything? Did I get all the overlap? I think you got it. Well, a little bit. You can. All right. Questions there? Yes, sir.
Would it not appropriate shading as she answered the question?
Great question. The actual, this is the solution. This is how you have to, this is how we have to state the solution for an inequality of the system. Okay. I'm going to have to graph it. Because it would be very difficult for me to use, say, interval notation because I've got some weird things going on with some x values, right? And y values. So I can't use interval notation because I have to do it graphically. What other questions? There was another hand over here. All right. What about your turn? Oh, yes. Let's try this one. So we've got a linear, actually we have two linear functions. The y's, horizontal lines, one of them going through 0 and one of them going through 3. Both of the boundary lines are solid. So I have, oh, yeah. So here's the going through 0, 1, right on the axis, and then 3. Yeah, what straight lines you draw. Let's change the color. All right, there they are. There's our y equals 3, y equals 0. Boundary line solved. The next one, y is less than x squared minus x minus 2, quadratic. And so if I want to graph the quadratic, I need to go find my axis of symmetry. Negative b to a. I get 1/2. There's the axis of symmetry, vertical line going through 1/2. I'm plugging that back in to find the y value of my vertex. You get 1/4 minus, let's just make everything fourths. So 1/4 minus 2/4 minus 8/4 gives me negative 1/4 minus 8/4, which is negative 9/4. Or negative 2 1/4. It's probably easier for us to graph it if it's decimal. So my vertex with an HK value of negative 0.5, 2.25. Did you guys have that? Switched them up. See, there we go again. I just always have to do something. But thanks for catching that. All right, there we are. So we're going to go there, and I actually, because I have a factorable, I have an x minus a 2 and an x plus 1. I actually also know my x-intercepts, or my zeros. They're going to occur at negative 1 and 2. So negative 1/2, or positive 1/2, negative 2 1/4. So positive 1/2, negative 2 1/4, yeah, right about there. Looks good. And then negative 1 and 2, crossing at negative 1, crossing at 2. And then I could, at this point, I don't need those x-intercepts. What I could have done is, because I have a vertex, and I have a situation where I don't have vertical stretches or shrinks, there's no a term other than a 1, I could have again used my critical movements of left 2, up 4, right 2, up 4, left 1, up 1, right 1, up 1. And anyway, I would get my curve. And this is also, oh no, wait, this was not solid. So there's a dash we're going to apply. So we're going to get something that looks like this. Okay, signs sorry, not signs. Shading. Let's do the quadratic since we're still here. Less than. Again, test a point. Let's say 0, 0 for a test purpose. 0 less than negative 2, and that is false. So even if I test 0, 0 is false, I'm not going to shade inside. I'm going to shade on the other side. So I'd be shading here, which is the same thing as the less than portion of that graph. And the two linears, I'm bouncing in between 0 and 3 and here. And then, where is it in common? So we're good all in this area. And in this area. Is that what you guys had? As I was peeking around.